Hi, Chem 141. So today I'm going to try to teach you Lewis structures and how to draw them. So here's a couple of pictures. This is a caffeine molecule, and you can see at these little junctions are carbons, and that's oxygen, nitrogen. It doesn't show these little lone pairs, but this is kind of an example of a really fancy Lewis dot structure. And so eventually you'll understand these and be able to draw them. Okay. So it's good to kind of understand electron configuration for Lewis dot structures. Potassium is an example here. It's in the fourth row on the periodic table. So if you look here, 1, 2, 3, 4, the fourth row. Here's the potassium. 1, 2, 3, 4. So n equals 4. So then you can see it has n equal 1, 2, 3, 4. So the fourth shell is the outermost shell, and that's what you call the valence shell electrons. So you can see this number here correlates with that 4s1. And the periodic table is chunked up into these blocks. This is the S block, this is the P block, and this is the D block. Those are the main ones you have to worry about. The F blocks here, we don't use that too much if you go into nuclear chemistry and stuff like that. Okay, so that's the 4s1. And so 4s, and then 1 is the first square. So 1, 2. This would be 4s2. So 4s2 is calcium. You can see that right here. So that's all those numbers mean. I'll go into them a little bit more on a different talk, but just so you know, that's kind of, they're here on these slides. So looking at the valence shell electrons, for example, sulfur, it's important to know that they come from the S and the P block. So sulfur is over here. And if you look at the n equals 3 row, 1, 2, 3, there's 3 s2 electrons for up to magnesium, and then 1, 2, 3, 4, 3 s4. So 3 s2, 3, sorry, p4. 3p4. That'd be sulfur. So if you look at these here, you can see the valence electrons. So 4 plus 2 is 6. So it's like the sulfur atom disappeared. But so we can do this for boron too. Oh, it's over on this side here. Whoop, there it is, sulfur. So excuse me, 1, 2, 3, 4, 5, 6 electrons here. So you can see those there. And so this is a simple electron dot symbol. So if you do electron dot symbols, you can kind of get a feeling for how to do Lewis dot structures. Here's boron. Boron is right here on the periodic table. And so this is in the n equal 2 row. So you count 1, 2, 3 electrons over. So that'd be 2s2, 2p1. So you count those 2 plus 1 is 3 valence electrons. So you have boron, and you can put them around like that. 1, 2, 3 valence electrons. So here's the electron dot symbols for the first 20 elements. Carbon and nitrogen and oxygen are some of the more common ones that you'll want to be familiar with for these type of molecules like caffeine or cholesterol. You see hydrogens here, oxygen, carbons are obviously here. And then this one has nitrogens, the caffeine molecule. Okay, so here's some electron configurations for some different atoms. You see calcium here. Calcium's over here. So if you count 1, 2 valence electrons, so the highest number here is 4. So it's got 2 valence electrons. You can do this Nobel gas configuration where it abbreviates that. So argon. So it goes all the way up to argon and then to calcium. So that's the stuff after argon. Argon would be 1s2, 2s2, 2p6, 3s2, 3p6. So you can see argon's right here. And so you go 1s2, 2s2, 2p6, 3s2, 3p6. So the next one's potassium. So that'd be 4s1. So it goes argon, abbreviating all this stuff. And then 4s1. So that's kind of what that's about there. But what this is useful for is you're able to find the valence shell electrons. So for example, vanadium, find the highest row, 4, and so it's 4s2. Vanadium is a transition metal, so it's a little funky with its d electrons. But okay, so the Nobel gas configurations are all here. 1s2, 1s2, 2s2, 2p6. So you can see that they all have 8 electrons in their outermost shell. 4, 6 plus 2, the 5 shell, 6 plus 2, the 6 shell, 6 plus 2. So if you look on the periodic table here, they're all in the 1, 2, 3, 4, 5, 6, 7, 8th column here. So that's where they're most stable. So thinking about that going forward, this affects the type of bonds. There can be ionic bonds and covalent bonds. Those are the ones we'll mostly be focusing on. And there's also metallic bonds. So to understand ionic bonding, you have to understand what's going on with sodium and, or like, for example, a metal, the transition of electrons. So sodium's here. You can see the n equals 1, n equals 2, n equals 3. So it's spitting out this electron. And so that would be the Na plus ion. And so that 3s1 electron, it's readily lost. And now it has the Nobel gas configuration of neon. So you can also think about this in terms of chlorine. Chlorine has 5, 6, 7 electrons. 1, 2, 3, 4, 5, 6, 7 in its third shell. So you see at 1, 2, 3 shells. So if you put one more electron in there, you'll end up with this chlorine ion. And that's going to be similar to argon's electron configuration. You see it has a full octet. So that's kind of what these different atoms want. They want to have that electron configuration. So what happens here is that the two atoms will come together, sodium and chlorine. So the sodium ion's here with its +1 charge, and the chlorine ion's here with its -1 charge. Sodium lost that electron, so chlorine's happy to take that electron. So maybe this is the electron that got put here. So it transfers the electron, and then they have this charge imbalance, and then they electrostatically bond. So like sodium, if you draw the simple Lewis structure, and chlorine, 7 electrons, 1, 2, 3, 4, 5, 6, 7. It wants that octet. Sodium will give the electron away, and you'll get Na plus, and then Cl minus. 1, 2, 3, 4, 5, 6, 7, 8. Put that minus on the outside of the parentheses here. Good. So this is kind of in a way, this is a Lewis structure for ionic compounds. You put that little bracket there. Okay, so here's the periodic table again. You can see here the metals over here on the left, and the non-metals are on the right. So there's the metals, metal, and then the non-metals. So the non-metals tend to gain electrons, becoming like the noble gases, and the metals tend to lose electrons, becoming like the noble gas in the previous row. So what happens with covalent bonding, non-metal, non-metal? So that's where Lewis dot structures come in. So maybe I'll stop this video and then we'll keep going so you can kind of watch this in 2 parts.